Hi everyone, today I would like to make a presentation about an experiment journal with the title of Optimization of Instrument Conditions for the Analysis for Mercury, Arsenic, Antimony and Selenium by Atomic Adsorption Spectroscopy. So, the objective of this experiment is to determine the optimizations of instrument conditions according to some parameters for the analysis for mercury, arsenic, antimony and selenium by hydride generation atomic adsorption spectroscopy. Actually, the chemical vapor generation atomic adsorption spectroscopy is a technique which is extremely popular for the trace analysis, specifically hydride generation continuous flow system for arsenic, antimony and selenium, and also cold vapor for mercury. Okay, for the objective of optimization instrument parameters is because this will improve the sensitivity and reliability of the experimental results. Secondly, it will also increase the productions of hydride or vapor species form, thereby improving the recoveries. In addition, it also helps to reduce the chemical interference from other species that may compete with the analyte of interest for hydride formation. What is the parameters that including in these optimizations? The first one is the flow rate of reagent. Second, sample flow rate, eigen flow rate, acetylene concentration of reagents, and also read delay time. Now, let us go into the results of optimization. The first one is the optimum concentrations of reducing agent use. The optimum concentration of reagent use for arsenic and antimony was 0.6% weight per volume in sodium borohydride in 0.5 weight per volume sodium hydroxide. Whereas for selenium, the optimum reducing agent was 0.1% weight per volume sodium borohydride in 0.5% weight per volume sodium hydroxide. The most efficient reducing agent used for mercury is well established to be stainless chloride, and the concentration was found is 25% weight per volume stainless chloride in 20% weight per volume in hydrochloric acid. For antimony and mercury, it was observed that high concentrations of reducing agent use achieve better signal intensity. However, for the arsenic and selenium, greater signal noise is produced with the increasing concentrations of sodium borohydride. The second is the concentration of acid reagent use. The higher the concentration of acid reagent use, the higher the hydride generation process can occur. However, elevated acid concentrations produce larger amount of hydrogen gas, which can dilute the hydride vapor, thus decrease the concentration of hydride produced. So, an optimal acid conditions is essential for different trace analysis. According to the results, the acid conditions for the hydride generating elements is as follows, which is 5 mole for arsenic and 10 mole of hydrochloric acid for antimony and selenium. Next is the flow rate of acid and reductant use. The tubing for the sample is kept constant, and the pump tubing for reductant and acid were varied. After obtain the maximum signal for the acid and reductant, their pump is remain constant in size, but now the sample tubing is varied in order to find the maximum adsorbance at once. Higher flow rate resulted in higher signal intensity, so increase in sensitivity. However, overflow can result in the concentrated yet unstable vapor and decrease in signal intensity. The optimum flow rate for reductant and acid for all the metals is 0.96 ml per minute. the maximum signal was obtained at a sample flow rate of approximately 7.0 to 7.05 ml per minute for arsenic and antimony and selenium, while the maximum for mercury was obtained at approximately 6.5 to 6.7 ml per minute of the sample. As the carrier gas, the flow rate of the argon should be high enough to strip the volatile hydrides from the liquid mixtures and carry them up to the sample cell. But it must not be so high as to dilute the hydride form. According to the result, the optimum argon flow rates for arsenic and mercury was 0.2 ml per minute, while for selenium and antimony, the optimum argon flow rate was 2.0 ml per minute. Lastly, the metal ion present in these hydrides can adhere to the surface of various tubes that make up the VGA77, causing memory effect. In order to effectively remove these adhere ions, an appropriate flushing time, which can be controlled by the instrument delay time, is needed between the samples. The delay time was optimized to ensure that the possibility of the memory effects was eliminated. Arsenic, antimony, and selenium produced maximum signal at lower delay times of 20 seconds. However, mercury requires longer time, which is 70 seconds, to eliminate the memory effect. So, these are all the summary concluded about this experiment and the results obtained in optimizing instrument conditions according to some parameters for the analysis for mercury, arsenic, antimony, and selenium by hydride generation atomic absorption spectroscopy. Thank you.